Okay, we have to start first. Okay, come. Guys, take a look at the two worksheets, right? Okay, I have given you guys two worksheets. You'll be doing questions from both worksheets now. Okay, later on. Okay, but take out the set 7 first. Okay, that one we are going to focus on that first. Yeah. Okay. So once done, right? Okay, once you're ready, let's just do question 1. Okay, I need you guys to do question 1A. I'll give you guys about 7 minutes to complete. Okay, just 1A up. Okay, if let's say you finish ahead of time, you can try the other worksheet, right? That's why I give you guys 2 today. Oh yeah, this. Oh, you have it here. I don't think you want 7. You have 2. Okay, we are doing set 7 now, by the way. You can just do your question first. Okay, those who are done ahead of time, just you can try the other worksheet of questions. Right? I highly suggest you draw a table, ICF table for part 2, right? Okay, just about 3 more minutes left. Okay, just this page. Yes. I don't know, that was just on the own time, just move it there. One more minute. Time's up. Okay, very quickly, let's go over the question. Okay, then let you guys move on to part B afterwards. Okay, so 1A, right? I tell you guys, whenever there's any buffer questions, please resort to drawing tables immediately. Okay, ICF tables must be done in most also. Okay, that's the best way to showcase this. Once you have drawn the tables, right, you're 90% done with the question already. Okay, so first of all, let's answer part 1. Part 1, they are saying, right, that they have a buffer consisting of these two species. Okay, acid conjugate base pair, and then now they are adding base, right? Okay, when you add a base, you must react with the acid, and it will produce a little bit more of the conjugate base. Okay, so that's your first equation. Okay, just go and write that down. Okay, plus OH minus. Okay, take note, this is an acid-base reaction, so please check that there's a full arrow, and then finally you get back the other species. Okay, and then there's water also. Okay, so that's the answer for part 1. Quite straightforward. Just make sure your arrow is full and all that. Just copy down this same equation in part 2 because we're going to start off with this anyway. They are going to add strong base into this existing buffer also. So we're just going to plot a ICF table in moles. So let's just quickly convert all the volumes concentrations into moles first. Okay, they did tell us that the acid they added 0.001. And then the conjugate base is 0.0015. Okay, those are the existing starting reagents. Okay, the starting amounts. Then afterwards, they also added base. Now the base they added is 14 cm cubed, so 0.0014 moles. Now if you notice something, right? Usually when you see these numbers, okay, what's the next thing that you must find? You must then find the limiting reagent, right? Okay, because these two guys are going to react, and now the limiting reagent is the acid. Which is a little bit odd because if you guys know your buffer questions well, you will realize that your strong base should be the one that's limiting. Never mind. Okay, let's just follow the question. If the acid is limiting, you just fill up the rest of the table. You don't have any more acid remaining, but you have a little bit of strong base left, but you're going to produce a lot more of the conjugate base. Okay, so these are the values that I have currently. Is this a buffer right now after the reaction? Okay, I have these two species. Do these two species constitute a buffer? No, right? Okay, it's not an acid or conjugate base pair. Now, do we just stop over here? Do we just find the pH of this OH minus? No, because I hope you all realize, right, that this guy can also undergo another round of deprotonation. So in other words, the remaining OH minus can actually deprotonate this guy one more time. So I'm just gonna bring another table into the question, right? This guy will deprotonate one more time to give me the final deprotonated species. So let's just transfer these two values down to my next table. Okay, my initial amount of this guy, 0.0025, 0.0004. I don't have any of the base to start off with. So all we're going to do now is to repeat the same process as the beginning. Okay, you just need to identify yet again the limiting region. Now the limiting region is the strong base, which makes a bit more sense in the context of a buffer. Okay, because once you fill in the rest of the table, you will notice something, right? You will notice that you do not have any more strong base. You will have the conjugate base, and you minus this off, you still have the acid remaining, 0.0021. What do you notice over here now? Okay, if you realize, right, is this a buffer? Yes, so after the entire reaction has settled down, right, finally settled down, you will get a mixture of the acid and the conjugate base, and that is the buffer. It's just that now the buffer consists of the different pair of acid and conjugate base. It doesn't consist of the initial starting pair, basically. Okay, so what you're going to do now is that 90% of your working is done already, if you notice. Okay, so table, very, very recommended. Now you just need to find the pH of this buffer. pH equals to pKa, 1 or 2, by the way. Is this pK1 or pK2? It should be pK2, because you notice now I have the second pair of species, which is your pK2, plus log conjugate base over acid. Now go and identify this second pair, who's the acid, who's the conjugate base. Okay, and once that's done, you can get your final answer of 3.56. Okay, so take note, right, for those who kind of struggled with this question, please take note of your ICF table method, especially for buffer questions like these. Okay, and also one small little thing, okay, just make sure that this concentration is in concentrations. So you just divide by volume, don't just put your number of moles in there. All okay with this? Yeah, right? So again, please go and retry this question, especially if you struggle a little bit more with it. You just need to plot tables, especially for buffer questions. ICF tables is the way to go already. Okay, Ken? If there are no questions, right, okay, let's proceed over to part B. And part B, there are 3 parts. I'm going to give you guys slightly more time because there's a bit more calculations to be done here. Okay, 3 parts here, just go and finish up the rest. Okay, so I'll give you guys about 9 minutes, okay, for the next 3 parts, or 10 minutes now. Right. Mole. Yeah, right. Everything is in moles. Right. Which part do you don't get? Okay, see, I started off with these 2 amounts. This is what the question started off with. Right. If I add this amount of base, you say 14 cm cubed, so I convert that to moles. Right? But from the first reaction, okay, your base is actually in excess. There's excess base, right? Which will then react with this guy one more time to get rid of all the base. So at the end of the day, the base will be 0, right? But you end up with a separate pair of conjugate acid base pair. So then that's why we need to use pK to decoupling. If you draw a table, Okay, you see two with okay. Okay, again, don't spend too much time on part one. It's a 1 mark proving version. Cannot just move on. Okay. We have about 5 minutes left. Part 2 is a very normal selective precipitation concept. Okay, nothing special in part 2, so please make sure you get it correct. Right? Okay, for those attending part 3, it's not as scary as it looks because the question only asks you to find 2 things. Use those 2 things and you can get the answer on, right? They said table 4.1, the data there. In your answer in part 2. You can find these 2 things, you can calculate the answer already. Right? I repeat for part 3, since most of you guys are there now, right? Okay, just find the 2 things that they want you to find, and you can work out the answer, right? Okay, we've got 1.5 minutes left. Is there? That's not the correct thing. The answer for part 3 might look weird, but ask your answer, right? Give you guys 1 more minute. Finish up. Then we take the answer. Very much. I think you put the wrong key. Think probably somewhere like that. Okay, I'm gonna go over the answer now, right? I think this is a rather well set question now because they took selective precipitation and they kind of changed things up a little bit. Okay. Now, start from the beginning, guys. There's one fat paragraph they give you guys at the start, right? Now, in this fat paragraph, I need you guys to just highlight that purpose. Okay, that part is very important. Okay, because usually, guys, in a selective precipitation question, they will ask you guys which salt precipitates first. That's usually your job, but now they tell you. Okay, so they told you guys that they want to achieve the max amount of Ce3 plus precipitated. What does that mean? Okay, you must instantly make this connection here. It means the Ce2, okay, this cerium salt over here, is the first and only to precipitate out of the solution. The other contaminant, which is calcium 2 plus, is never going to get precipitated because that's what selective PPT is all about. You only want one guy to precipitate, and now they tell you which guy it is. Sometimes, okay, most of the times they ask you to find that using calculations, but now they tell you first. Okay, so we'll come to that later, but okay, let's just look at this diagram first for part 2, right? Selective precipitation, you have to kind of use this as a visualization. Okay, you are adding C2O42 minus slowly, so it becomes more and more concentrated. Okay, but there are 2 checkpoints. The first checkpoint is which guy ends up precipitating first. And because we already made that link in front, we already know that the cerium salt is the guy that precipitates first. And then you keep adding, you keep on adding. The second point, right, is where your calcium begins to precipitate. This guy precipitates second. And you do not want him to precipitate because that's the idea, right? Only one guy gets to come out. Okay, so we'll come back to that later. Okay, let's prove part 1 first. How do we prove part 1? sometimes, right, guys, it's all about writing things down. When you write things down, right, you can eventually see what to do. Okay, you stare at it blankly, right, nothing's gonna come. Right? So first of all, right, they asked us to find the KSP. Okay, so basically I want to find the KSP of this calcium salt. I'm just gonna write it out. Okay, a normal KSP expression just looks like this, right? And the second thing that you need to do is to look at the data, right? The data gave us some weird looking K. What does this K represent? Yeah, I hope you all realize this K is just a normal KC expression. Just your typical products divided by reactants. I'm just going to change this to K out. So from log K, I'm going to change back to K. And let's just write the expression for this particular equation. Now, they wrote it in this manner. So how do we write our products over reactants? Is there a product here? This product is a solid, right? Okay, solids cannot appear in any case. So it's just 1 divided by the reactants, which are equal. So those reactants can be considered inside. So this is actually the expression for the Ks they gave us in the table. Now, by writing these two values out, right, I want to find KSP. Okay, so this value of K is 10 to the power of 8.63. Now, out of habit, don't go put a minus sign there. Okay, there's no minus, only here. Okay, then what's the link between the two? To find the KSP, and I only have the data here, what should I do here? It's just a reciprocal, right? So in other words, KSP is equal to 1 divided by K. Then you can sub in your values. Then you can get your final answer. So take a look, guys. Okay, this is a show question. You need to have all these things out. So this is what, okay, this is how I wrote the answer basically. This is what I want. This is what they gave me. And this is the link between the two. So that's what you need to do also. Okay, write down what you want. Write down what they gave you. You can see the connection straight away. Very, very obvious. All right. Okay, so that's the answer to this question. All good, huh? Okay, no concept involved, is more of math. All right, then let's look at part 2 now. Part 2, I already said you must know how to do this. Okay, because it is the fundamental of selective precipitation. You must always find the minimum concentration to precipitate each salt in order to find out which guy usually comes out first. But now they tell you already. Okay, so we use that information to confirm our answer later. And remember, whenever you want to find the minimum concentration, you must equate IP and KSP. That is like the minimum condition for precipitation, right? So I'm just going to do the first one for calcium. Okay, so it's easier to calculate. Okay, then just sub in the KSP value that you found just now. Okay, and they told you guys the concentration of calcium 2 plus. Just divide by 0.01, you can get 10 to the power of -7. Okay, so this is the value needed, right, to precipitate the calcium salt. Repeat the same thing for the cerium salt. Okay, write down the IP expression first. IP expression a little bit, a lot of powers and a lot of powers over there, right? Okay, so just be careful. Okay, but once you have done all of this, right? Okay, go and do the square root. Okay, you can get this. Okay, and I want you guys to look at the significance of these values. Don't just like look at it for fun. Okay, sometimes they can ask you guys to determine which salt precipitates first. And it is always the one that is a lower concentration needed that precipitates first. Agree with that? Okay, so here they told you already, so your answer must correspond to that at least. And we're going to use this for part 3 as well. Okay, but that's pretty much your selective precipitation concept. All okay with this? Yeah. Now let's look at part 3, right? I'm just going to use the question, whatever they ask me to find. Just write it out first. Okay? They asked me to find 2 things. And guys, this question, I hope you all understand what's going on now. Usually for selective precipitation, you add this concentration of C2042 minus yourself. So you manually go and add inside slowly, right? Progressively. But now, right, this C2042 minus comes from oxalic acid. There's 1 mole per dm cube of this guy, right? Just sitting inside the solution. And this guy will produce what you need, right? To selectively precipitate these 2 salts. So it's going to happen by itself. And to simulate that, you need to have a certain pH value. So I'm sure you all can see already, right? The data from the table is obviously this equation because this is the only thing for me to find pH. So let's just write it out first. Okay, so before that also, right? Okay, let's just convert. Okay, H plus square C2042 minus divide by reactants. Okay, and this is equal to, okay, let me just convert this. Don't forget the negative sign here. Negative 5.06. Okay, by the way, I hope you all know this, right? This is not a Ka expression. Okay, even though this is an acid, this is not Ka because it doesn't differ by 1 H plus. You will never see this in a K expression. You will never differ by 2H plus at once. Okay, but anyways, okay, coming back to this, right? They asked us to use our answer in part 2. Okay, so what answer do we use? We got 2 answers there. Okay, go and highlight the words maximum amount, okay, to precipitate the max amount of C3 plus. And this is where our diagram will help. Where is the maximum point of precipitation? Is it here? Next, serum salt. Is it there? Do we stop there? No, right? Okay, because this is only the beginning. This is the start of your precipitation. Only a little bit starts to come out. Then where do you stop? That's the question. Where's the maximum you can go? Remember, it has to be at the other point. This is the end. Basically, the maximum you can go to, because you can't go beyond that. You go beyond that, you end up precipitating 2 salts. And that's die already. Your whole experiment just gone wrong. Okay, so this is the point that I want to be at. And I know the minimum concentration at that point is for calcium. So you must take out this value, okay, for maximum precipitation. Okay, so again, to precipitate maximum, okay, you have these 2 values in your answer. So I've taken out the 2 things the question want me to find already. And can you see to find H plus, right, just need to sub everything inside. Okay, to find concentration of H plus, I have this value, and oxalic acid is 1 mole per dm cube, which is already given to us. Now, this is where things get a little bit weird. Okay, you might doubt your answer also. The concentration of H plus, right, is 6.1 mole per dm cube. A very, very high number, right? So when you go and find your pH, answer here is negative 0.785. Take note, right? When you see a negative value, I'm sure some of you guys initially doubted yourself. You're like, what the hell? What's going on? How come got negative value? Okay, I hope you all realize, right? Negative pH is definitely possible because you clearly got an answer there, right? Okay, negative values are possible, right? Why is that so? You're going to try playing around with your calculator. Any concentration of H plus larger than 1, right? You will get a negative pH value. Don't believe you're going to try. Okay, because usually our H plus is at under concentration of 1. Very, very small concentrations. That's why negative log, you get yourself a normal positive value. Okay, anything bigger than that, you rarely see. Okay, that's why this value looks very weird. Okay, so in A levels, if you get this, just trust your answer. Okay, don't go and doubt yourself. Right? Any questions here? Okay, so those who struggle with this, okay, please go and redo this question. I think it's quite well said. Right? Other than that, okay, we can just move on to the next question. Okay, so come, I want you guys to look at the second question now. Okay, this VJ question. Just do part A for now. Okay, just do part A. There's this idea of atom economy that I want to discuss. Right, okay, so A, there's 4 parts. Okay, I don't think it's only very long. Yeah, I think like at most 7 minutes can finish already. Okay. Those finish in advance, you can just try the other worksheet also. And just maybe a little advice on the definition of atom economy that they've given, right? I wouldn't really agree with it. It's a little bit ambiguous now, right? Okay, but just a tip, right? Your answer should be relatively large. Because they did say that this is a environmentally friendly reaction. And a reaction that's environmentally friendly has a high atom economy. That's what they say lah. Okay, so your answer should be reasonable, okay, reasonably high. Okay, so if your answer is very low, right, that means you probably calculated wrongly. Yeah, it's one of the about 2 minutes left. You must get part 2 and part 3 correct. Then that's a guarantee. Okay, but part 1 and part 4 is some new stuff. That one is okay. But you struggle a bit more. Okay, 1 minute left. That's why I said a little bit. I understand that this is more of measuring how efficient your experiment is. If you say it's a measure, how much of this is actually running in one? Not because you're turning this one. So you're in the process, you keep turning this. Okay, come. Let's stop the time there. Okay, let's go through this question. Yeah, I just want to let you guys do this question not because it's tough or anything. Okay, but it's more on to introduce this idea of atom economy. I just want to clarify this because I don't know, like environmentally friendly and stuff is like becoming quite in now. So it might come out for the paper. Who knows? Okay, I just want to clarify what atom economy means. When you all say, okay, the numerator of atom economy is very obvious, right? The molar mass of ibuprofen, which is what you want, is 206, so it's 206 on the top. Okay, but at the bottom, right, when they say sum of all the products, okay, you guys will, I don't blame you guys, because that's my first instinct also. You just add up all the different products together. But you can't simply do that, because if you go and calculate all the MRs and you add together, you realize the denominator is very large. And a large denominator means the atom economy is very small, which again doesn't make sense because they say this is environmentally friendly, is what they claim. So the value of atom economy must be quite high here. What does it really mean? Okay, to put it more into perspective, they did say, right, it's about how efficient your experiment is. Okay, these are products that you eventually want to achieve the final product, right? But in the process, right, this is actually your waste, if you can see that. You never needed CH3CO2 hit. It just came out as some sort of a byproduct, which doesn't contribute to the final product. So that is the other product that we are actually discussing. So everything in the process, you're not supposed to count all these. It's just the final product plus any wastage, which is just the MR of ethanoic acid. Then you can get your answer like 774. It's about 77% efficient. So 20% of that has been lost to ethanoic acid in the process. Okay, in case this concept does come up for A levels, right, I hope you all have a better idea. Because I don't really like the definition as well. Okay, it's very, very weird. Okay, I don't think it's an accurate way. Okay, Ken? Answer for part 2, I don't think I need to discuss this, right? Okay, it's just your electro sub because you are substituting onto the benzene ring. Straightforward. Okay, part 3, let's just discuss all the possible answers, distinguishing tests. Yeah, I don't think it's hard as well, right? Okay, A is a secondary alcohol, ibuprofen is a carboxylic acid. Okay, one answer you can probably use sodium carbonate, which will distinguish your carboxylic acid. Okay, any other answers here? Okay, isoform test, good. Isoform test is for this, particularly the methyl alcohol, right? And there's one final answer. What is it? Sorry. Okay, dichromate, yes, but KMnO4, no. Okay, why KMnO4 cannot? Side chain oxidation, yes. Okay, take note of that. I must be very careful. Anytime with benzene rings, you must always pause and think whether KMnO4 is suitable. And here it isn't. Okay, just be very careful. Okay, and part 4 is just a follow-up of part 1. Okay, so I want you guys to make some sense of the answer before you get it. New atom economy. So what they did over here is that they said they can actually recycle the wastage. You can see that. Okay, they recycle ethanoic acid and turn it into ethanolic anhydride, which is this. Okay, this equation here. Okay, let's just write out what they told us. Okay, you need 2 moles of this. Okay, so I'm taking the waste and I'm recycling it into something useful. You can see that. Okay, so now can you all see, right? Okay, what is the other products? What's the wastage in the process here? Okay, or you think about it, if there's a recycling of the waste, right? Should your atom economy go up or go down? It should go up, right? Because you have just used your waste for something useful. So your answer has to be higher. Okay, but do we count this as the waste? No, this is useful item. Okay, I want this for the reaction of this flowchart, right? Instead, your waste is now just relegated to just water, right? Water is a lot smaller, so that means the amount of wastage has to be less. Okay, so how do you calculate the new atom economy? Okay, we just take 206 over 206 plus what? Is it 18? No, here's 9. Okay, why 9? Because it's only half a water molecule, as you can see here, because of this little 2-ethanoic acid thing. Okay, look back at this thing. 2-ethanoic acid gives you 1 water. So 1-ethanoic acid only gives you half a water, which is very little wastage. So your answer here is very high, it's about 95% or something. I think it's 958 if I'm not wrong. Okay, so next time when in case you see this same idea again, right, in the paper, just know what atom economy is. Okay, it's just things that didn't contribute to the other products. Just things that didn't contribute to your final product. Everything else, all these is what I wanted also. Okay, Ken? Now with that said, okay, you can just proceed over to part B. There's nothing too crazy about this question also. Okay, part B, just do the whole 3 parts. Okay, this one shouldn't take very long also. I think 8 minutes will be enough. Okay, 8 minutes for part B, 3 parts. use in the because see, right, when we make design product, we need design. All these are leading up to the design product. So it's even including the what comes because everything is leading up to the design product. Not really look at the final end product, which is just even more for MR schools. And now, right, what we do now is that we took some of these and get them recycled and regenerate this kind, which is something that is part of the pathway to lead to the design product. And then I never counted it when we start. Right? Okay, based on the formula, they say it's only the final product. If you're talking about the diesel, then no, not trying to count the ethanol and hydrogen. It's not waste, it's useful. But water doesn't actually contribute to the pathway. Just like this guy here, doesn't contribute to the pathway, so it's useless. Useless things then you add on to the additional denominator. When two of the P the use of structure of PCL 5 it's not PCL then 4 or 5CL. So yes, we have yes. Only one come out, so 4 still stuck. So this is how PCL 5 looks like. They try not to spend too much time on the mechanism. There's another 3 marks on the next page, which are a lot easier to get. You will see where it is like. Okay, but for part 2, right? Okay, just maybe I can give you guys a bit of hint for part 2. Okay, they ask you to consider bonds form. So it's some sort of energetics concept. Is there any energetics concept, right, that talks about complete reactions? What does a complete reaction mean? Very favorable reaction, right? Okay, very good favorable reaction. Usually, what kind of conditions will lead to that? How does a bond form an energetics concept then link towards a favorable reaction? Okay, so perhaps you use that, right? Try to make the link. In other words, look at the most significant bond that was formed in the equation, right? Yes. Retry. You must specify reach the whole. So it's too much specified, but yes. Wait.
Later 1 to 7, Nigel and what's his name not coming? Omi. We'll be together with like one single J1 if you come. You want to come tomorrow instead? 4:30 to 6:30. That's true. Or you want to come on Sunday?
Come today.
From 5 to 7 with the one J1. Hello?
Yeah, I'm going to do the synthesis. The synthesis is very free, 3 marks. Okay, so make sure that's done also. Okay, keep a bit more time. Okay, you realize that the 3 marks in the mechanism versus 3 marks in the synthesis, you realize which one is more worth it now, right? Okay, by the way, for the part 3, right, the printing cutoff lah. Ibuprofen is a carboxylic acid. Just refer to the first page. I don't know why there's a cutoff towards the end. Okay, please do the synthesis. Don't know part 2, never mind. Okay, 1 more minute. Okay, we're gonna stop the time there. Okay, give you guys a bit more time already, right? Okay, I'll look at the mechanism first because I realize some of you guys are spending a bit too much time on the mechanism, which I hope you all realize that in the exam, right, go and do the synthesis first lah, definitely. Prioritize synthesis because it's a lot faster for more marks. It's very value lah, basically. Okay, for synthesis, right, okay, first of all, go and position your reactants. And they said the oxygen must attack the phosphorus, okay, just follow suit. Okay, the lone pair on oxygen attacks phosphorus, and then it causes, okay, because phosphorus can only form 5 bonds maximum, right? So now that you form a 6th bond, that's not possible. So you must break 1 bond over here. Okay, you can even show your partial charges to show that the ridge is attacking the pole. Okay, so that's what we have for the first step. That's it, right? Okay, so you just need to bond with the phosphorus. Now take note, right? The oxygen still has the H attached to it. Nothing happened to the H yet. Okay, so PCl4. Okay, but oxygen is giving lone pairs away, right? Losing electrons means he has a positive charge, and then you get Cl minus, which then balance out the positive charge. Okay, so that's for step 1. Done. Okay, and moving on to step 2, just bring your intermediate down. Step 2 is a lot simpler because they told you guys what the Cl minus is used for. Okay, the Cl minus is used for deprotonating the H. Okay, so just do the same thing here. Lone pair on Cl minus attack the H, and then the lone pair, the bond pair give back to the oxygen who needs it. Okay, that's your second step. Done. Right? Okay, so you have this now. Okay, so oxygen has no more charge, but he still has the PCl4, HCl. Okay, so HCl is the byproduct that appears in the end of the equation also. So that's where it came from. Okay, the last step is the one that's a bit more tricky because there's a lot of things happening. Okay, there are 3 arrows for you guys to draw, quite a lot, right? Okay, and just read the question carefully. Let me just bring my intermediate down first, and before I embark on the question, let's just draw out all the products and whatsoever. Okay, the product that since this is the last step, the last step must give you the final product, which looks like this. So in other words, okay, your Cl minus must be bonded to this carbon, and that's what's happening in the first sentence. The carbon is getting attacked by another Cl minus ion. Where does this Cl minus ion come from? Just draw, because they say another, right? So it's external lah. You just follow the instructions here. So what can it attack? There's only one carbon to attack, which is this, because that's your eventual product that you want to form. So that's one arrow done. Can you see that? Okay, next. Okay, we also need to form POCl3. Always refer to the top. Okay, POCl3 has a double bond O and only 3 chlorines. Now it has 4 chlorines, and they did say PCl bond is broken. So PCl bond broken to get your Cl minus. Can you see that? Finally, PO double bond. Where do we form the PO double bond? as you can see here, right, okay, the PO is now single bond. I need to add electrons to it to form a double bond. But where does it come from? Okay, as you can see, this carbon and oxygen bond needs to break, right? Because it's not there anymore. So break already, and where do we give the electrons to? Just nice, this PO double bond wants a second bond, right? So give it to him now. Yeah. Okay, I know there are some variations. Some of you guys, right, might have done this. You point to oxygen first, then from oxygen you point to the double bond. Now, I can't fault that, right? Okay, it's correct also, but there's a faster way. The faster way is just point one arrow, settle. Okay, that. So 3 arrows done, okay, then you can get all those as the Cr minus will eventually cancel out. That's why it doesn't appear in the overall equation. Okay, any questions here? Yes.
I go and have the Cr minus that they jump out, right?
Yep.
Can I use that to work?
Okay, yeah, okay. So this is what I initially thought also lah. Okay, initially, right, okay, because they said by another Cl minus ion. Okay. Some of you guys never add this external Cl minus ion. I don't blame you guys because there's no Cl minus in the equation, lah. Okay, so what you all did, right, is that you take this and then attack this, is it? Yeah, okay, that's what I initially thought also, lah. Okay, but let's try to follow the instructions here. They said by another Cl minus ion. This isn't a Cl minus ion technically. Okay, so your electrons here shouldn't jump straight to attack that carbon there. Yeah. Okay, and yeah, I think I kind of agree also that why not this one break already, right? Then this one becomes Cl minus, then this one attack this one. Yeah, okay, that's what I thought also, but apparently that's not what happens. Okay, but that one a little bit, I will accept it as well, but honestly, okay, because but based on the question, this is more accurate. Okay, Ken? Okay, so that's for the mechanism. Okay, let's look at part 2. Part 2 is quite interesting, right? Okay. Now I gave you guys a bit of hint just now. Look at the bonds formed. You must look at a very significant bond that's formed. Okay, there are many bonds formed, but there's one that's very significant. And how does that lead to a very complete, very favorable, very spontaneous reaction? Okay, you paraphrase a bit. This is where you're supposed to be looking at. Now, bonds formed is an energetics concept. So we probably have to talk about enthalpy at some point. What bond should we be taking out first? What's the most significant bond that's formed here? The PO double bond. Okay, so you should mention that in your answer first. Okay, the PO bond is formed, which is very strong. Okay, this is the most significant bond. Now you can mention other bonds lah. Okay, go ahead, but you must minimally have PO double bond in your answer. How does forming a very strong bond lead to a very favorable reaction? Okay, let's break it down slowly. We said it's an energetics concept. A very strong bond means the enthalpy change is what? Very highly what? Exothermic. Good. Okay, highly negative, highly exothermic. Bonds form, okay, very strong. So the delta H is highly exo. Now, guys, think about it. We are slowly trying to talk about why this reaction is super favorable. A very exothermic reaction means what? Very exothermic reaction. Think about energy level. Okay, that's we talk about that later. Okay, that's correct also, but we talk about that later. Okay. A very exothermic reaction means the product is very stable. Yes, okay. Exothermic reactions means the product has very low energy level. So you can mention that products have low energy level, making them very stable. And guys, a very stable products, is that favorable or not? Yes, right. Okay, you want to form stable products. So all the more you want to form it, right? Okay, so just mention that in your answer. Okay, so hence reaction is very, okay, you can paraphrase a little bit, okay, don't just copy down the answer. Okay, it's very favorable reaction. You can see it's very spontaneous, okay, and that's why it's very complete. Now, this is an answer that you can't find in the answer key, but I think it makes sense also. If you talk about what the answer key also mentioned, it's a little bit harder to spot, but it talks about spontaneity. Okay, so they have this part of the answers still there. Okay, PO double bond, highly exothermic. But what does a highly exothermic reaction mean? Okay, that's when they actually take a look. They took out the delta G equation. Okay, you can talk about spontaneity also. So in other words, what's happening here is the delta H, since it's highly negative, delta S technically is positive, okay, because you form more of the products. Okay, that's why the delta G is highly negative also. So that's what they mentioned. Okay, the delta G, very spontaneous, and a very spontaneous reaction, they also mentioned this. Okay, let's write down. Okay, highly spontaneous, and they said KC very large. Now, don't expect you guys to write KC in your answer. I know they talk about how the extent of the reaction, completion, right? Okay, so KC is viable here, but it's not even a reversible reaction, so I don't expect you guys to have KC in your answer, but that's another thing you can consider as well. Okay, next time, if you want to justify whether a reaction is very complete, right, you can talk about KC, yeah, okay, even though it is not a reversible reaction. You can, that's an option that I'm going to open up for you guys also, okay, but I will prefer this answer personally. Okay, Ken? Okay, and part 3 is honestly, you see these 3 marks, right? Please go and get it in the exam. Okay, don't ever skip synthesis, it's the easiest. Okay, what's the functional group in the intermediate? Nitrile, done, settled. Okay, how do you know nitrile? Because okay, it's a step-up reaction, 1 extra carbon. You can only mean nitrile. Now remember, synthesis got cheat codes, so I'll tell you all the cheat codes already, right? Okay, mechanism, okay, there's no cheat code around it. You just have to be very slow and meticulous. Okay, but yeah, you got the answer here already. Please settle. 3 marks in the back. Okay, ethanolic KCN heat and H2S4 heat. Done. See, these 3 marks took me less than 30 seconds. Okay, you can do it as well. Okay, synthesis can go up to 5 marks. Those just spend a little bit more time, right? 5 marks in the back. Okay, so answers over here for part B. Any questions so far? Any issues? Okay, okay, we don't have time for part C, okay, but I want you guys to now move on to question 3. After this question 3, I'll tell you guys what to do, right? Okay, then we take a break later. I still want to move on to the other set of notes. Yeah, okay, so come look at question 3, right? Do A, B, and C. Okay, part C is especially important. It's about E0 values. Okay, so question 3, A, B, and C. Give you guys about 9 minutes. Okay, this is a pi bond that you're talking about. But if you say it's weaker, right, that means you're comparing, right? The first thing I think of is you're comparing to a sigma bond. Right, but when it's weaker than sigma bond, what significance does it have? How do you elaborate? Okay, when you compare pi and sigma, you should be talking about electrophilic addition. Like electrophilic addition, right? Okay, why do you electrophilic add, right? You don't need heat one, right? It's because pi bond very easily broken. But the sigma bond doesn't break because sigma is stronger. But over here, there's nothing about the pi bond, right? Just only the pi bond break. It's just the bond as a whole. So if you look at it as a bond as a whole first. Yeah. So as a whole, right, you're forming a double bond, not just a pi bond. It's very strong. Okay, so that's the idea. A and B are very content, right? You know what to write, okay, can just spam, right? if for part C, the question isn't demanding, you don't need to write balance equations or whatnot. They only want you guys to write E0 cell and observation. So you don't have to write down things that they never ask you guys to write, right? Okay, 2.5 minutes left. Okay, and time's up, right? Okay, just gonna go over the first two parts for now. Right, so I wrote the answer for both part A and part B on the board. Right, I just want to talk about part B. Okay, part A is a standard answer. Variable oxidation states always because of this. Yeah, done. Okay, so that's just content knowledge. Okay, but for part B, right? Okay, I just want you guys to take note. Why is the answer so long, right? It's because they ask for significantly higher density. Okay, so you can't just tell me like one simple factor. If the density is significantly higher, okay, take a look at your mass over volume. It probably means that both mass and volume, right, will contribute to a higher density. So which makes sense. Okay, you talk about mass, probably going to be higher. The volume is probably going to be smaller, and that contributes to a way higher density. So you need to talk about quite a few factors here. Okay, and the main reason, right, is actually under your volume. Okay, why are transition metals? Why do they have much smaller volume? It's because of this first big chunk over here. I first thought about how 3D and 4S have similar energy levels. So they both can contribute to the sea of delocalized valence electrons. Where am I getting at? Okay, so first of all, take note, it's only valence electrons in a metal, right, that can be delocalized, not all the electrons. So specify valence. What I'm trying to get at is the vanadium or transition metals in general, right, have stronger metallic bonds than an S block metal like calcium. How is this related to density? Okay, so take note, right? Having stronger bonds means what? That means the atoms have to be more packed closely together, right? Okay, so they are packed more closely together. Okay, simply because now the atoms, right, okay, can be held more tightly. Okay, so imagine this, okay, all the atoms are more squeezed in, right? Okay, it means that overall the lattice is much smaller. Okay, the volume of the lattice is smaller, contributes to a higher density. Okay, but it's not just that. Even though this is a very significant reason, let's talk about all the other reasons that contribute to a higher density. Okay, another one will be relative atomic mass, right? Okay, the mass is higher because the AR is higher. And at the same time, they also gave us data on the atomic radius. Okay, the atomic radius is smaller as well. Okay, take note, smaller atomic radius and closer packing are two different things. Okay, I'll just quickly mention first. Okay, so I said together with vanadium's smaller atomic radius and a higher AR, sorry, that's why the density is significantly higher. All three things point towards one idea. Okay, so you need to talk about a lot of things here. Okay, the main reason why it's much higher is actually because of your strong bonds leading to closer packing. Okay, so take note, right? Closer packing means the atoms are legit squeezed together very, very tightly. Okay, but for smaller atomic radius, we're looking at a singular atom. One atom, right, is just smaller in size. Okay, so compared to calcium, calcium is much larger and it is not packed as closely together. Maybe got some gaps on. Yeah, okay, so that's the idea behind both. Okay, both ideas point towards a smaller volume. Okay, can visualize the difference. Okay, yeah. Okay, just content knowledge. Okay, from now density questions are take note, it's not as simple as it seems to explain. Okay, but now we take a look at part C. Okay, I'll tell you guys how to solve for part C type questions, right? Okay, rather quickly. They never ask you guys to, okay, don't write too much because they ask for observations and E0 values only. Okay, don't write balance equations, they never ask. Okay, so for the first question, right? Take note, guys, whenever your CH2O2, it can be either reducing or oxidizing. So you must consider both possibilities. Okay, if it oxidizes, right, oxidizes to O2 gas, the E0 value is 0.68 volts. If it reduces instead, right, it reduces to water, and then it has a much higher E0 value. Okay, again, you can't determine which is which now, right? Because you need to look at the other guy. Okay, the other guy is BO2 plus, which has an oxidation state of +4. So there are two possibilities here. So it could go higher, right? And higher is your +5 oxidation state, which is this two over here. Or it can go lower. Okay, it reduces to V3 plus. Okay, it's just one difference. Okay, this value here is 1 volt. This value here is 0.34 volts. Okay, so I'm just taking out all the data that I can possibly find. Now, what is the reaction that happens here? You consider a pair, right? If H2O2 oxidizes, VO2 plus must reduce. Can this happen? Reduction minus oxidation, the value is negative. So you scrape this already. It's out. This doesn't happen. But you consider the other pair, reduction minus oxidation does happen, right? The E0 value is positive. So that's the answer. Okay, no equation is needed. Just give me your E0 cell. 177 minus 1 give you 0.77 volts, which is more than 0, and you just need to tell me that it's spontaneous. That's your 1 mark. And then your second mark is observations. Okay, H2O2 to water, no observation, no effervescence, nothing. But this guy here, you just refer to the color chart. I already told you guys before that vanadium don't need to memorize colors, they will give you one. Okay, so over here, vanadium 2 plus is blue, oxidized to a higher state, which is yellow. So what's the color change here? Is it just blue to yellow? It's accepted, but not as good. Okay, I want you all to take note also. I talked about this before. The solution turns from blue to green, then finally to yellow. Okay, I also told you guys before to acknowledge this idea. The reaction isn't instantaneous. If it's instantaneous, then sure, blue instantly turn to yellow. But no, it takes a while. So in that period of time in between the start and the end of the reaction, there's going to be a mixture of both, right? And blue, yellow give you green. Okay, so this is the recommended answer. Okay, the answer close one eye accepted blue to yellow also, but I really feel you all must have an intermediate color. Okay, I also talked about green to violet before, if you all remember. You know what's the color in between green and violet, like a mixture. Okay, it's like gray or brown also accepted. Okay, again, this one not as obvious as this one, right? Okay, but now I'll talk about the second part, right? Okay, this part here, why did they give 3 marks for this? Why is that more demanding? Okay, so again, the allocation is this. This is 1 mark, the color also 1 mark. Okay, let's take a look at tin. Now take note, for tin, right, you can find 2 equations, but for the tin metal, there's only 1 equation in the whole data booklet. It can only oxidize to SN2 plus, it can't reduce, right? Okay, so this value here is negative 0.14 volts. If this is oxidized, that means this one can only reduce. Okay, you don't have any other choice, it reduces to a lower state D3 plus. Let's see whether this is possible. Answer is yes lah. Okay, the reduction minus oxidation gives you positive value. Okay, so we write that first, so this one quite obvious. Okay, this is positive 48, more than 0, spontaneous. Okay, so everything is fine so far. You can tell me what's the observation. So VO2 plus to V3 plus. Is there any intermediate color here, by the way? Blue and green got one middle new color. The answer is no lah. Okay, so if there's no middle color between blue and green, right, it's just bluish green. You don't need to mention it. Okay, so just tell me blue turn to green. Okay, so tell me that first. Okay, solution turns from blue to green. This is the only time where you don't have to account for the intermediate color. But after doing all this, you realize the answer is very short. Okay, you only have 2 marks. Okay, where is the final mark? Here. Very important idea. How do I get my final mark? Yes, you must prove that you can't go any further. Why did I not do that for the first part? Okay, you realize I just did 1 equation, settle, finish. Okay, because you all realize something, come back to the first part here, right? This equation, you oxidize to +5 oxidation state. And 5 is the max. You can't prove anything beyond that one, right? Okay, you don't have a choice. But here, there is a possibility that this guy, right, can, okay, it reduces first, this one can, but you do not know whether he can reduce even further to V2 plus. And you need to check. Now, from first glance, maybe you say, oh, cannot, right? Okay, you compare the values. But from now on, please take note. Okay, make a mental note. Whenever you're proving reactions like questions like this, you must get to a point where it becomes not spontaneous, then you can stop. Okay, now cannot stop yet. Okay, so this value here is negative 0.26 volts, and you realize reduction minus oxidation still gives you a negative value. And take note, guys, the keyword here is also excess. That means tin will still be there for it to oxidize, then this one can still reduce further. So that's the 2 things you need to consider. Okay, you don't consider tin 2 plus to tin 4 plus. Okay, no. Okay, you're still using tin. Okay, so last but not least, okay, E naught cell. Reduction minus oxidation. You get the negative value, then you can stop. Okay, not spontaneous. Okay, then just give me one final statement. Okay, this part is 1 mark. Okay, so the solution, or you can just tell me V3 plus does not reduce further to V2 plus. So the solution just remains green on. I want to talk about observations, right? Okay, so you just say solution remains green. Okay, this final part over here then is your final mark. Okay, I know it's not intuitive, right? To prove something that doesn't work, so you all don't want to write it, but must write lah. Okay, no choice. Okay, all good. Okay, right. Okay, part D, part E, you're going to do yourself lah. Okay, I don't think I have time for that today. Okay, we shall take a break first. Later we do the other set. There's some questions I will go through from there. Okay. Any questions you all can just ask now. Yes. Halogen derivatives. Towards the end, like this. Always a segment that our notes also have. Guys, let's continue. Okay, we started quite late today, so we'll end around the same time as that. Okay, so I want to do one question from the other set. Okay, take out the other set, right? And we're gonna do question 2. Okay, selected parts in question 2, we're gonna try those. Okay, so guys, can you look at question 2 and just do part A? Part A only has 2 parts. Okay, I'll just give you a bit of time to just try it, right? Okay, so about maybe 5 minutes. Take out the extra set up in question 2A. What did I hear? Okay, 2A has two parts. Okay, next page also have. Okay. They only ask you guys to use the PKB values, right? Compare PKB values, then you look at these equilibriums, right? Okay, about 2 minutes left. With all the leading groups in reaction 1 and 2, we're gonna write down the PKBs for each one of them, then go and compare, right? What does a bigger PKB mean? What does a smaller PKB Okay, just one more minute for those to finish up the answer. If you're done, you can just proceed to part B, I guess. Okay, I think most of you guys are done, right? Okay, let's go through the answers. Okay, especially part one. I want to go through part one. Quite interesting question. Okay, the idea of leaving groups has been talked about in our syllabus before, but I think they removed it at some point in time. Okay, but leaving group is about a nucleophile. Okay, they give you a bit of information. Okay, they will teach you guys along the way also. Okay, so let's understand what part one is talking about. Okay, what is a leaving group? Okay, they said this sentence over here. Okay, so this mechanism here, right, is all about attacking and swapping nucleophiles. The nucleophile come in, Y comes out, okay, and then we just have a swap lah. Basically, it's just a substitution. Okay, so as you can see here, right, what does it mean when, okay, they say when the base is stronger, when the leaving group is a stronger base, the poorer it is as a leaving group. What does it mean to be a poor leaving group? Or conversely, you can ask yourself, what does it mean to be a good leaving group? So Y is the leaving group because Y left, right? Now, if you are a good leaving group, if you leave already, will you come back? No. Okay. A good leaving group leaves already and doesn't come back. Okay, like any normal person would. Imagine like this, someone break up already, right? If you are a decent person, you break up already, don't come back. But if you are a poor leaving group, what does that mean? You break up already, then you try to get back together with the person, right? Go to harass the shit out of the person. So it's the same thing over here. If you are a poor leaving group, and that's because he's a strong base. So perhaps we can start here. If you are a strong base, what does that mean? A strong base means what? Okay, based on our idea of our knowledge of basicity. Okay, a strong base means the lone pair of electrons are more available for donation, right? I mean, that's just nothing new, right? So if you're more available for donation, again, how does that link to a poor leaving group? You take a look at the final step here, and you realize all these are reversible reactions. The more available the lone pair, can you all see, right? There's a higher chance of it attacking back this carbon. Is there anything stopping it from attacking this carbon here? No, right? In fact, if its lone pair is more available, the chances of it attacking it, right, and reversing the reaction is much higher. And then they just get back to the start. Basically, he never really left, right? Okay, he leave already, but he ends up coming back, which is a very bad leaving group. A good leaving group has to be something that is weak. Because if it's weak, then the lone pair cannot not strong enough to attack. Okay, then if he cannot attack, then he can't get back together. So that's the idea here. Okay, so in other words, you just need to tell me, okay, the more available for donation, okay, it is more likely, okay, for Y minus to attack the electron deficient carbon, reforming the starting compound. This is the main part. Okay, a bad leaving group, right, will reverse the reaction. That's why you get back the starting reagent. So that's the principle behind this question. Okay. OG, yeah. Okay, so that's for part one. Okay, so just be prepared. Leaving group is a concept that's very close to our syllabus, but it's not really in our syllabus. That's why this kind of questions might come up. Okay, let's go to part two. Okay, first, any questions for part one? Because usually part one I see a lot of varying answers. If anyone would like to ask. Okay, if you don't have, I'll just proceed to part two. Okay, so part two, right? Some of you guys might find this question a bit familiar. Okay, so let's understand the requirements first. They ask us to compare PKB, and PKB values are all given to us. I'm just going to write all the PKB values here. This is -2, this is 9, this is -2, and -24. Okay, they're saying that reaction 1 is better because it will produce this guy better. Right? Okay, but how does that work? You compare the first reaction. What's the difference between the PKB values? This guy is lower, right? A lower PKB value means it is a what? A lower PKB value makes it a stronger base, right? Which means in comparison, this guy has the higher PKB value, making it a weaker base. Can see that? Now guys, if you compare between the two, a stronger base on the left, a weaker base on the right, who will win? You can think of it as like a tug of war like that. Okay, stronger base on the left, weaker base on the right. Of course, the stronger base is more powerful, right? So if the stronger base is more powerful, that means it's dissociating in the forward direction. In other words, the POE of this equation lies towards the left or the right. The right, right? Because the strong base will dominate. On the other hand, right, you all look at the second equation. Here, the smaller PKB is this guy. So this guy ends up being the stronger base in comparison to the other guy. This guy now has the larger PKB, making it the weaker base. Looking at reaction 2, right, where does the POE now lie towards? Considering that the stronger base will dominate, now his backward reaction will be favored instead. So now the POE of reaction 2 will face the left-hand side. And do you want it to shift to the left? No, because I want to produce this guy, so you want the POE to lie to the right. So in other words, this question here is like balancing scales like that. Okay, the stronger base will win the weaker base. So you proceed in the direction of the stronger base. That's the main idea of this question. Yes. Okay, so I got this also. Okay, the previous class, someone asked, can we use the leaving group idea? I would say no. Okay, why we don't need the leaving group idea is because number one, the question never asks us to refer to that. And number two, right, the idea of a leaving group is this. In order to leave in the first place, right, you need to be together first, right? So you together with someone already, then you can break up, right? Okay, but this they were never together in the first place. So it's not really appropriate here to use the word leaving in this case. True lah. Okay, but then you look at this here, right? When they substitute, right, it's actually more on this guy leave, this guy take his place. This one, okay lah, it is true lah. Yes, okay, this one really kind of, I guess it swaps with this guy, right? How will you explain this? Sorry? Okay lah. So you're saying that now he's a stronger base, he's a poorer leaving group, right? So wouldn't it come back? This but it's contradicting the question mark. They say reaction 1 is more favored, so it should be lying towards the right. You see that? Then reaction 1 is a better method than reaction 2.
You cannot say that this, like, because the thing that comes out is like this part, right? So it's a better, right? So it comes out.
Okay, you see the you see the idea here. Come back to the first part, right? Poor leaving group will come back and reverse the reaction. A poor leaving group is usually the stronger base. Now you take a look here. The stronger base here, okay, if this is the weaker base, it means, okay, it is a stronger leaving group, right? Okay, actually, okay, why is this guy here, right? Okay lah, fair enough, like leave really doesn't come back, right? So it doesn't shift. You say shift to the left, that's wrong. Yeah, okay, but you could say yes. Weaker base making it a stronger leaving group, so it doesn't come back, right? So that's why the POE lies towards the right. Okay, fair enough. I'll give you that also. Okay, but if you're not very comfortable with the idea of leaving groups, which we aren't really that comfortable with, right? Then try to use the PKB idea. After all, they might not agree, they might not give you the mark, right? Because they ask you to use PKB values. But yes, the leaving group idea does kind of work also. I could accept that as well. Oh, because you made this connection here, is it? Okay, fair enough also. Okay, any other possibilities here you want to consider? Okay, but mainly, right, this question, right, you don't even need to talk about leaving groups. You just need to see, right, okay, between strong versus weak, the strong will dominate. So it's mostly about position of equilibrium. You can just jump straight to the idea. All good with this? Yeah. Okay, any more questions you want to ask about this? You can ask later. I want to try one last question. Okay, so can you guys look at part D? Okay, part D. So a little bit on the organic separation. Okay, this one we rarely ever do now. Okay, so give this question a bit of thought also. Okay. Question 2D. Right. Just give you guys about 4 minutes. Yes. It means. It means yes, but it's not it means. Now it means not soluble. So the fat then again, that's a very general statement. It depends what carboxylic acid you're talking about. Right. The carboxylic acid is very big, and clearly it's not soluble, right? The carboxylic acid is small and can. Same thing for amines. Small amine dissolvable, soluble, yes. But it's not a small amine. Right? Of course not. It's a separation, purification. Guys, you're separate already. You still need to obtain them as the original compounds. So whatever you react with, if you don't turn it back, then it's not complete. You get. Okay, so you have, okay, both are now solid, right? If they are both solids, you cannot just filter them yet. You must make one of them a what first? Yes, dissolve again, liquid, right? Okay, so you make one of them a liquid already, the other guy must still remain as a solid. So in other words, you need to find a reaction that makes the product, right, of either P or Q soluble in water. Okay. So you think about it, P is an amide, Q is an amine. Which one can react to form something that is soluble in water, right? We have one more minute left. Okay, you must know your reactions well between amines and amides. You know it. You order chicken, then you eat. Okay, your answer has to have a little bit more explanation inside also. So not just steps. Okay, let's just go through this question here. Okay, so P is amide, Q is amine. Currently, they're both solids. how do you make one of them a liquid? And which one do you make a liquid first? What do we add? Acid. Okay, guys, when it comes to phenylamines, part of the purification process is by converting it into a salt. Okay, so that's the first step to this question. Okay, what you want to do here is to add your aqueous HCl, and then you can just stir the reaction, stir the mixture. Right? Okay, so a little bit of practical steps in here also. Then what's next? Once you stir already, P still remains as a solid because amide can't dissolve in an acid-base reaction, but amines can, right? So next thing is you must tell me what is formed, right? Okay, so now okay, the solution contains what? Okay, you can just tell me the salt of Q. You can draw the salt of Q as well. Okay, I recommend this. So the salt of Q, right, will look like that. Remember, this is a base getting protonated, so you add a H plus to the nitrogen. So now the nitrogen has a plus charge also. But let's just explain, guys, why can this dissolve in water very quickly? What kind of interactions does it form with water after turning into this? Ion dipole. So you can just very quickly tell me which can form favorable ion dipole reactions with water. That's why it's soluble in the first place. Okay? Then what's next? What's the next step? After you've done your explanation. What's next? Oh wait, you haven't filtered them yet, right? Okay, we need to separate them first. Okay, so now you just filter the mixture. Okay, and just say with a dry filter paper, okay, whatever. Dry filter paper, dry filter funnel. Not that important here, okay. This is not really the planning question. Okay, then what's next? After you filter, I always tell you guys you must specify a couple of things. What's the filtrate and residue? You tell me this very briefly first. Okay, so the residue contains what? Okay, residue is your solid, which is just P, whereas the filtrate contains what? Okay, please be careful. The filtrate doesn't contain Q yet. The filtrate contains the salt of Q, which I'm not done yet. A lot of you guys stop here because, oh, look, separated. Okay, no, you want to try to obtain them in the original states, right? So I want to get back Q. Currently, I have this. How do I get back Q? Just add NaOH. Yes, okay, and that's part of the process of, okay, you all know your thin excess concentrated HCl and heat, right? And then afterwards, they add NaOH. It's because you have the salt. You want to take out the salt, you must precipitate it. Okay, so now, right, the final thing is you add aqueous NaOH to the filtrate. Hey, just explain a little bit, okay? Forming back, okay, the solid Q. That's the whole process. So you it's assumed to obtain back the original item lah, okay, not the derivative of the item. Okay, can? So this question here just take note of in the future. Yes.
Like can use other.
Usually it's HCl lah. Other acids are let me consider. Refine lah. HNO3 refine. HCl is a commonly used lah in this process. HCl is supposed to be can. Yeah, we can as well. Safest here will be HCl because that's what we normally use. HNO3 should be fine as well, I guess. Yeah. Okay, if you want to stick to it, right? Okay, we always stick to convention. Conventionally, we use HCl equals for phenylamine reactions. Yeah. Okay. Any last questions here? If not, right, okay, that's it for today already. Okay, you can go and complete the rest of this worksheet also. Okay. Yes. Yeah. Okay. Can yes. Mapping students. But now we have a soluble insoluble white percent. But you still have oh, one equals. Yeah, one equals. Right. Then it doesn't dissolve in water. Hydrolyzation, they get different items. It's not the individual, but you are live, so get anything because best is big time on see. I get it, get it, you know, eating as because you know, eating as settle. The method yes, sir. On strength and stability, it's not really. Yeah, I mean, see, yes, the form effective on the logo, that's not wrong. But you got on strength. Strength of the font, how do you relate it to the same? You definitely you got just. You might. A strong bond, okay. That's why it's strong bond. But later, the healthy very so it's like low energy level. You go to half the years. Yeah, the fact is now you have to find a bond. But you just strong bond. More energy to form the normal. That's why it's about exothermic reaction. So at the end of the day, it's still going down. Yes. Yeah, I mean, yeah, it is on.